Okay. So I am starting to pop on at 5:30 every day just because it does seem like I'm getting a lot of questions, and it's Calc 1. It makes sense. Students tend to be more conscientious in Calc 1, and when they have questions, they advocate for themselves better and they actually ask questions that they have. So that's good. I don't want to leave you hanging. So I've been logging on at like 5:30. If I log on at 5:30 and like my kids usually nap till 6, and sometimes my husband doesn't get home till 6, it's very slightly possible that I could log on at 5:30 and have to log off again, but I would let you know. They're not like infants where they have to have me every second, but it's, they can't be completely unsupervised either. But it should be fine. It should not be a big problem. So if you have questions and you want to pop on early, go ahead. If you think you might have questions but you're not sure, I know sometimes I used to have students who would just come into office hours just because they wanted to hear what everybody else was going to ask, because they weren't really sure if they had any questions, or maybe they thought they were okay, and then if something came up that kind of they were like, oh yeah, maybe I was not sure about that also, then they found it helpful. But that's up to you. I know it's a long time to be on a video call, so it's available to you if you wanna come. Were there any other questions on the homework?
I just have a general question.
Sure.
Are we gonna go over the video that we watched over the weekend, or are we gonna start from 1.4?
We are going to start from 1.4 unless you had questions on the video. So I'm just kind of leaving the video up to you. And then if you have questions about it, you can email me over the weekend or ask me like before class, or ask me now if you have questions on it. But I hadn't really planned to do anything else from the video.
Okay. Yeah. Thank you.
You're welcome. Morgan, do you have a question?
Yeah, this is just like a question about the class. Do we have class July 5th?
I don't know. What is July 5th? Let me look at my calendar. Oh, as far as I know, we do. A Monday. Oh, I see what you're saying, because on my calendar it says Independence Day, like, observed. I did not receive notification from ACC that it's a vacation day, but I will double check. I have a pad that I keep here to write down questions that students ask. I'm almost positive we have school, but I will double check. So sorry to burst your bubble. Yeah, it's always nice during a summer class when July 4th falls during the week, and then we get to cancel a day and kind of get a little bit more R&R, but I don't think that's the case this year for July 5th. Were there other questions? So does anyone have any general feedback about the asynchronous weekend stuff? This is my first time ever doing that. I mean, I have recorded asynchronous videos before, but I haven't actually like built it formally into my class. If you wanted to state anything about it, you can, or you can always email me. Like I said, I try not to make it too long because I know it's a long time to sit through something asynchronous, and I do go through it a little bit faster, but that's because you have the option to like pause it and kind of work at your own pace. The feedback that I've gotten in the past from students about asynchronous videos is that some of them really do like it for that reason. Some students, especially students that take maybe a little bit longer to like get through the work and maybe don't feel as comfortable with the topics, they really like that they can just kind of pause it, rewind it, and then keep going, and they don't feel like they get left behind like maybe they would in class. But I know it's kind of up to you, but it looks like everybody, I don't know for sure that everybody watched it, but it has like 59 views. So I think that's a good thing, because I have posted asynchronous videos before and I've had like 10 views on it, and I'm just like, okay, so clearly you guys didn't watch this. But it's built into your class, so hopefully we'll all be responsible about that. And your quiz did cover the topic, so that's good. All right, anything else before I start 1.4, or finish 1.4, I should say? Oh, someone had emailed me, I think it was Connor, I don't know how I lost it though. He emailed me about the test. You know what? I bet you it's in my other email. If you email my ECC student email, I see it. I don't know. I see it differently, but clearly I knew he had emailed me, so I knew it was somewhere. Oh no, he was asking me about the final exam. No, the date for the final exam for your class is actually July 29th. So that will be your final exam, the last day. So I don't know what I'm going to do for asynchronous time that last week. We'll have to see. Kind of have to see how that last week goes. Your first test, though, is scheduled, and it's on the calendar for the 17th of June, which is Thursday. So I'm going to write that down. It is important. So test 1 is going to be Thursday, June 17th, and it's going to be during class hours. You're going to have the whole class time to take it, so you don't have to worry about like finishing and then starting a new section after that. The only thing is you will have the test on Thursday, and then you'll have the asynchronous stuff that weekend. But the nice thing, I know we don't like having tests Thursday because it's kind of the end of the week and stuff kind of rushes at you. The nice thing about that, though, is the asynchronous work that you have on the weekend will be a little bit lighter because it'll be the start of a new chapter, and the start of a new chapter is always lighter. So, so there'll be that. If you're wondering what's going to be on test 1, it's definitely going to cover 1.1 through 1.5. It's kind of depending on how long it takes us to get through 1.5, because it's a little bit of a longer section. We might include a little bit of 2.1 on it. And normally I wouldn't include another chapter's worth of material or another section from a chapter. However, the material from 2.1 and 2.2 goes along with chapter 1. So kind of depending on where things fall, I sometimes just put that in the chapter 1 test. But we'll see. We'll kind of see where we end up. I don't want to throw too much at you and then give you a test on Thursday. So it might be easier to just test you 1.1 through 1.5 and then give you that asynchronous chapter 2 work over the weekend. Plus, the rest of that chapter is really very straightforward. Students don't tend to struggle very much at all in chapter 2. So I don't mind putting that in with chapter 2 either. Kind of just depends on where everything falls. But plan for your test Thursday, June 17th. Remember that I'm going to be proctoring you. This is a test where I'm going to be emailing you a PDF of the test when I see that your workspace is ready. So you're going to have your camera on the whole time. Oh, I'm going to add this to my sticky note. I'm going to email you about making sure that you are set up for your test. Email about workstation. And I'll give you just kind of I'll attach some photos of some workstations that I've seen that have been awesome. And just kind of some tips for how to get going quickly, because if your workstation's not set up, it's going to delay your test. So you might want to log on earlier on Thursday just so I can make sure that you're good to go. And then whoever I approve, I'm going to send the test out in batches. So I'll email it to your ECC Gmail. You can print it out if you want, or you can technically work on your own paper. It's a lot easier if you have a printer, but I know not everybody does. So, and then you're gonna scan your pages and upload them to a PDF, a single PDF file. So you should be making sure that you're ready for that and submitting them to D2L when you're done. So it will not be like the quiz that's on D2L. Your test is gonna be where you're actually gonna be submitting your written work and scanning it in with whatever app you want to use, or an actual scanner if anyone actually has we have an actual scanner, but I don't even know how to use it anymore. The software is like outdated, and I just use my phone to scan. We were scanning our mortgage paperwork with our phones years ago, so it's beautiful. It does really well. Okay, that's what I have to say about the test. I'm going to send you an email about your workstation set up so you have an idea of what to expect. Anything else before we begin with our continuation of 1.4?
Are we doing is the pre-calc review going to be on the test as well?
No, I'm only going to be testing you starting at 1.1. So yeah, okay. I'm not going to test you over pre-calc. You already were tested on that. at some point in pre-calc. Victoria?
Yeah, I just wanted to ask a quick question about the exam. How many questions are normally on there? Like, do you have like a range of questions that you normally put on an exam?
Let's see. I'm looking at the previous one. It's somehow miraculously like right in front of me. How many questions was it? It was like, 13 maybe? It was 13. Oh no, 14, 15. No, 14. Something like that. 13 or 14. Some of them have like A's and B's to them.
Okay, cool.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It was 16. Yeah, some of them are shorter, others not as short. The A's and B's are usually a little bit shorter. But yeah. I don't think you shouldn't have a problem getting it finished in 2 hours and technically 2 hours and 20 minutes. So you'll have the whole time, and some of you will be done in an hour and a half easily, and others will take the whole time.
Okay, all right, cool. Thank you.
You're welcome.
I had one more question. So on Wednesday, are we learning new material then too, and then it'll be on test Thursday? Or
My guess is that Wednesday we're just going to be finishing out 1.5. I might start 2.1 and then just say for 2.1 to not worry about it on your exam. But we'll see how far we get tonight. So yeah, technically there might be new material that you learn on Wednesday that'll be a continuation of what you're learning tonight. So it won't be like a completely new topic, but it might just be like the end of a topic.
okay.
Someone else, sorry, I missed who had a hand up. Oh, it was Burfin. Tell me, Burfin, what's your question?
Are we gonna have like a study sheet or no?
I'll give you one for the final, but not for your chapter test. But if you'd like, I can put up a WebAssign like review homework that's a little bit shorter that kind of covers a lot of different topics.
Yeah, that would be good.
Okay, yeah, I have one that I correlated to the book work because there's a review section in the book, and I think that's where I pulled everything from. I'll post that for you. I'm glad you reminded me. I'm going to add that to my little neon post-it. WebAssign review homework.
Thank you.
It'll be optional though, so you won't have to do it, but it'll be helpful. I know everything comes at us so quickly in the summer. Usually I would only see you twice a week. Okay.
Thank you.
You're welcome. Anyone else? Questions? Yeah, so the summer class it's kind of nice because you get it over with in half the time, but it's also a lot because there's not a lot of digestion time in between. But in some ways it's good because you don't really have time to like procrastinate or anything. Because we all are guilty of that. I know that I would procrastinate as a student if I had the chance. Okay. All right, so last time I talked about the squeeze theorem and how it pertained to trig limits. I want to give you now some basic trig limits that we're going to be using in 1.4. Okay, so the basic ones, I mean, these aren't anything too crazy. This is something that you would know just from what you know about trig. The limit as x approaches 0 of the sine of x equals 0. Well, I mean, by direct substitution, we know that the sine of 0 is 0. So that limit should be pretty intuitive for us. And then the limit as x approaches 0 of the cosine x is 1. And that's because the cosine of 0 is 1. So those are the basic ones. Now I'm going to give you a theorem that sort of pops off of these. If theta is measured in radians, then we have the limit as theta approaches 0 of the sine of theta over theta. Now this is also equivalent to the limit as theta approaches 0 of theta over sine theta. So this will work whether you're dealing with this expression or its reciprocal. This limit is equal to 1. Now this is the result of a proof that I'm giving to you in a theorem. So it's not something that you can just flush out directly using direct substitution. Note that sine of 0 over 0 would be 0 over 0, which is indeterminate. But the limit is actually 1. Now, there's a second piece to this, and it has to deal with the cosine function. So there's one more special trig limit. And this is the limit as theta approaches 0. Now, make sure we understand that in both cases, theta is approaching 0. This does not work anytime you have sine theta over theta, or anytime you have cosine theta minus 1 over theta. This one also works if we switch the order of subtraction to 1 minus the cosine of theta over theta. This limit is 0. Now, again, this is not something that you would be able to find using direct substitution. 1 minus the cosine of 0 would be 1 minus 1, which is 0, divided by 0 is indeterminate. But this is a special limit, and you are just being given this result, that the limit as theta approaches 0 for this expression or that expression is equal to 0. This is incredibly important. You're going to use both of these throughout 1.4. So make sure that you somehow note that they're special. I don't know, you can put a box around them. If you have a nice highlighter, you can highlight them. My highlighter is not that nice anymore, but it's not too bad. Make sure you can easily find that in your notes. When I was in Calc 1, my teacher told us a good way to remember these was that sine has an I in it, and an I looks more like a 1, and cosine has an O in it, and an O looks more like a 0. So if you find that helpful, as long as you remember the actual expression, and you just can't remember the limit value, that's something that you can use. It's important, though, that you just remember the expression also. But in both cases, you know that the numerator or denominator is theta, and it's either the sine or it's some variation of cos theta minus 1 or 1 minus cos theta. So a lot of times we're not going to be actually just given these particular expressions in our limits, but we're going to have to manipulate the expression in order to get it into these forms. And that's what I'm going to be doing in the next several examples. We're going to go over some trig limits. We'll talk about how to match this form, and then just sort of use some identities maybe, or some algebraic techniques in order to work with these particular limits. So I will give you example 2. Last time we did example 1, which was the squeeze theorem. Example 2 is just going to be find the limits. The first one will be the limit as x approaches 0 of the sine of x times the secant of x over x. So we're going to rewrite this limit just using some simpler expressions that we already know something about. What should be sticking out right now at you is sine x over x. Now, it's being multiplied by the secant of x, but the fact that it's being multiplied means that you can split it apart, and you don't have to worry about any sort of issues with your denominator because you're not adding and subtracting here, you're multiplying. And when you're multiplying, you can just multiply the pieces of your fraction without having to worry about how you're pulling those pieces apart. So we're going to rewrite this as the limit as x approaches 0 of the sine of x over x times, and then let's say you don't want to use the secant of x. Maybe we don't automatically know the secant of 0. That's fine. Remember that the secant of x is just the reciprocal of the cosine of x. So we can write this as 1 over the cosine of x. That is a reciprocal identity. It's one of the identities that's on that trig sheet that I posted for you on D2L. If you had trig last semester, hopefully this is something that is very, very fresh in your mind. But if it's been a few years since you've seen trig, this is just a reciprocal function. The secant of x is the same as 1 over the cosine of x, or vice versa. Now, once you've split up that product into these two factors, you can go ahead and look at each limit separately, because remember that you can take the limit of a product as the product of the limits. Now, you don't actually have to split the limit up and multiply them, but you can really just take each limit separately and multiply them together. Make sure that x is approaching 0 if you're going to use this first piece of the theorem that has to do with the sine function. And ours matches in this case. We have sine x over x as x approaches 0. It's going to match this first definition here in your theorem. So we know that this limit is equal to 1. And we can multiply that by the limit as x approaches 0 of the cosine of x. Well, we have that limit up here, but really you can just use that direct substitution. We know that the cosine of 0 is 1. So that would be 1 over 1. And again, how much work you show me here is kind of up to you. I don't need to see every little piece, but I need you to show me a reasonable amount of work so then I know that you actually like worked your way through this. And 1 times 1 is 1. Are there any questions on A? Renee, what's your question?
So wait, so you plugged in x, right? In the limit?
Well, for this piece, I just used the theorem. And I used the fact that this limit was 1. And then
Oh, okay.
for
You
this
switched it.
vector, I used, I just directly substituted it, basically.
All right, I see.
Anyone else? Questions on this one? Okay. You know, another thing I was going to say about coming in early for the office hour, which, by the way, we were told not to call them office hours. We're supposed to call them student hours, because when you call it an office hour, it's like students think it's the teacher's time and that they're bothering you. So I should start calling it student hours. But if you come in for that, I feel like I get to know you a little bit better, and I always develop a different, even online, I just develop a different relationship with the students who are constantly in the office hours. So you do start to just get a little bit more, I don't know, we build a connection. I get to kind of know what you know and don't know, and we talk things through, and you might find that you really enjoy that. And then you have to like deal with me having issues with technical difficulties too sometimes, but that's okay. B, the limit as x approaches 0. This function is, and we're going to use here this expression, cosine x minus cosine squared x divided by x. Now, when you're looking at that numerator, one thing I don't think you should do is split this fraction up using the common denominator. Because think about it. If you did that, you would have cos x over x minus cos squared x over x. And then you'd be stuck because you don't have anything that you can do with that. What you can do, however, is factor out one of your factors of cosine in the numerator. And sometimes these just take practice. Sometimes it's trial and error. It's kind of like when you were in trig and you had to prove those, like, verify the identities. And sometimes you just had to keep trying different things and seeing where you ended up. It can be like that here too, anytime you're working with trig functions. So if you try something and then you realize, like, wait, that doesn't work, just start over. You might have to try a couple different things for some of these. But factor out your cosine x. And remember, when you factor that out, you still have a 1 here for this first term. You should be able to distribute it back in and get back what you started with. And if you're wondering, well, how is this helpful? Well, now you have this guy, which is part of your special limit up here. So we're trying to recognize this when we see it. So the fact that we have 1 minus cos theta over theta in this form with x is going to be really helpful to us. So what I'm going to do now is I'm going to rewrite the limit. And again, we have a product, and we can just split up these two factors inside of our limit. So we have the cosine of x, and then I'm going to just use this x as the denominator for 1 minus cos x over x. Remember, when you're multiplying, you only use that denominator as many times as you see it. We just have x. I can't put an x here. Sometimes this throws students off. They're like, well, how come you didn't put an x down here also? I'm not subtracting or adding here. We're multiplying. I only have 1x that I can even work with. I've got to choose where it goes. And in my case, it doesn't make any sense to put it over here because, well, actually, technically, I'd have cosine. Oh yeah, then I'd have 0 in the denominator, which I don't want. That's why I'm putting it here. It matches my special limit. So this is your special limit, and then this one we're just going to directly substitute. So the cosine of 0 is 1. And then for our special limit, we're going to use this variation, which it totally matches. We're approaching 0, so we can use it. And that special limit is 0. And 1 times 0 equals 0. Okay, questions on B? Okay, let's do another one. So C is the limit as x approaches 0 of 1 minus the cosine x over the sine of x. Okay, now this one is actually very, very subtle. It's really one of the easier ones you're going to do, but it looks worse because you're thinking like, oh my gosh, I'm going to have to do all these crazy things to this problem. Actually, you're not. You're going to divide in the numerator and denominator by x. And, you know, the whole reason I'm going through a bunch of examples of this, and I'm going to go through a bunch of examples, is because I want you to get really familiar with different techniques that you can use depending on what your limit looks like. And even though you might not know when to use each one, you have a variety of things you can try. And if it doesn't work, try something else. And that's the whole point here, is I just want you to get a lot of practice. There are a lot of different things that can go on here. Now, the reason why you're going to divide by x is because if you do that, you're now creating a situation where you actually have both special limits. Now, x is approaching 0. That makes a big difference. That applies to our special limits. But here's a special limit. There's a special limit. Now you have it in the numerator and denominator. I mean, you could have spent 15 or 20 minutes trying to rewrite this in some sort of crazy way and gotten nowhere. And if you would have tried direct substitution, by the way, the cosine of 0 is 1, the sine of 0 is 0. You would have had 0 over 0, which is an indeterminate form. So that wouldn't have gotten you anywhere. But now you can use your special limits. I know that this one is equal to 0. The cosine has the O in it, goes with the 0. Sine I looks more like a 1, and 0 divided by 1 is 0. It's kind of like how you can multiply the numerator and denominator by any quantity over itself. You can do the same thing with division. You can divide the numerator and denominator by the same value. And as long as you're dividing each one of them by the same quantity, then you're not changing it at all. You're just writing it in an equivalent form. Questions on C? Okay. D. This is a really common trig limit type of example here. Sine of 5x divided by 3x, and we're looking for the limit as x approaches 0. Now, remember your theorem stated, and I'm going to remind you of your theorem because I know it's on a separate page now, that the limit as theta approaches 0 of the sine theta over theta equals 1. That's what we're going for here. But in order to use that theorem, you must have a situation where the angle of which you're taking the sine matches the angle in the denominator. And you don't actually have that here. In this case, you have 5x and 3x. Not the same thing. You need to make these match. These need to match. They don't currently match, but we're going to force them to match. One thing I want to make sure we don't do, I'm going to make a note here to you. The sine of 5x is not equal to 5 times the sine of x. Don't do that. You cannot pull the constant multiple off the angle and move it in front of the trig function. It doesn't work like that. You're taking the sine of an angle that has nothing to do with the actual amplitude of the function itself. So you can't do that. So don't try to do that. Try to catch you with these pitfalls that I know students tend to make. So what we're going to do, though, is we're going to force this to happen. So what I want is this, right? Here's what we want. I want to have sine 5x over 5x because I want the angle up in the numerator to match the denominator. And that's fine. I can make that b as long as I want it to be, but then I need to also keep the denominator I originally had. And if I want to introduce this quantity to the denominator, that's fine. I need to also introduce it to the numerator. So what we're really doing here is we're multiplying by 5x over 5x. And you're going to see that this type of technique is used often. I used it in part C. Actually, in part C, however, we divided by x in the numerator and denominator. In this case, I'm just multiplying by 1 in its special form, 5x over 5x. And if we were to cancel that out, which we wouldn't do, you would get back what you started with. Sine 5x over 3x, sine 5x over 3x. We've only just introduced 5x over 5x so that we can create this form. But now it matches what we needed for our limit. And we have these x's now that we're like, oh, wait, we don't even need these. This is redundant. Cancel out the x's. You don't need those anymore. And now that you've rewritten the function, you can go ahead and pop this back into your limit. So what you really have here is the limit as x approaches 0 of 5/3 times the sine of 5x over 5x. Now, whatever you do, don't cancel out the 5s. If you cancel out the 5s, you're undoing the work that you just did on purpose to create this situation where you have sine theta over theta. If you'd like, you can rewrite your limit and move this constant multiple in front. You don't have to, but it's an option that's available to you that might help you to see this a little bit more clearly. Before I finish this one, did anyone have a question about how we rebuilt this limit?
I have a question.
Sure.
I kind of missed how you got sine 5x over 5x. Didn't we multiply by 5x over 3x?
So kind of, mostly I had this wishful thinking going on, and I was just thinking to myself, wouldn't it be so nice if we had this? And I wanted this so badly that I made it be that. And then I just kept this 3x right where it was. And I said, okay, well, if I'm going to force this to happen, I really divided by 5x. I need to also multiply by 5x. So yeah, technically we could have done this slightly differently, where you could have started off with your original expression and then just multiplied by 5x over 5x. It just would have looked slightly different. But yeah, you could have thought about it that way instead. Personally, with something like this, I tend to start with what I want, and then I just force it to happen by saying, okay, well, I want to divide by this. If I want to divide by 5x, I need to also multiply by 5x to undo it. Does that answer your question?
Yeah,
Okay.
thank you.
I mean, as long as you can cancel it out and get back to where you started, then you haven't actually changed anything and you're okay. You've just written things in an equivalent form. All right, so now you can apply the special limit. We know that this limit is equal to 1. So we have 5/3 times 1, which is 5/3. So going back to Burfin's question, if you had instead started out saying, okay, well, we have this quantity, you could have then said, all right, well, I want 5x in the denominator, and you could have written it this way instead. It's the same thing because you still have a 3x and a 5x in the denominator. It's just that they're swapped. And you would have then said, okay, well, now I have this. I can get rid of those. And then you could have done the same thing by just moving the 5 over here and then moving the 3 over there. So same thing, slightly different thought process. Any questions on D? Okay. E, we'll work with the tangent function on this one. This is the limit as theta approaches 0 of the tangent of 3 theta divided by theta times the secant of theta. Renee, go ahead. What's your question?
Yeah, is your final answer for D just 5/3?
Yep, this is our answer.
Oh, okay.
Did it seem like a lot of work for just 5/3?
A little, but that's okay.
Well, I think it seemed like a lot of work because it was the first time I was showing you. If you were to do one of these on your homework, you'd probably be a little bit more concise about it.
Mm-hmm.
Okay. When you're working with a tangent function, you don't have to, but I would suggest switching that over to sines and cosines, especially if theta is approaching 0. Now, on your homework, you might see some problems where theta is approaching pi over 2, or theta is approaching pi, or anything that isn't 0. But if theta is approaching 0, you can try direct substitution first. That should always be your go-to, but a lot of these aren't going to work with direct substitution. Tangent of 0 is 0, and then if theta is going to 0, you have 0 over 0, which is indeterminate. And you do have those special trig limits. So personally, I would work on switching this to sines and cosines if I were you. So if you want to go ahead and pull the function out and work on it and then pop the limit back in, you might find that that's easiest because you don't want to have to keep rewriting that limit over and over again. Now, we know that there is a quotient identity for tangent. The tangent of theta is sine theta over cosine theta. And whether it's theta or 3 theta, doesn't matter. It's still just the tangent of an angle is the sine of that angle divided by the cosine of that angle. Sorry, I just noticed there's something happening in the chat. Oh, this was like forever ago. Okay, I think I addressed those issues. Sorry, I don't know why the chat does not beep for me, and I don't really see that tiny blue light at the bottom of my screen. Sorry. You might want to just like ask me a question. The chat's nice because the transcript gets saved in your Google Calendar, but if the transcript is just people asking questions that don't get answered because I don't see them, then it's really not that helpful. So yeah, I know, and some of our microphones don't work, and that's fine. I'll try to keep a better eye on it, I promise. Okay, so let's rewrite the tangent as sine 3 theta over cosine 3 theta. We'll focus on that first. And I feel like some people might be bothered by this. So if you'd like, we can rewrite the tangent last. I'm trying to write this in a way that confuses as few people as possible. Okay, let's focus maybe on first writing, keeping the theta in the denominator. We're going to move the secant of theta up as cosine theta. So as long as we switch its position in the fraction, we're using that reciprocal identity. So 1 over the secant of theta is the cosine of theta. And then we'll rewrite the tangent in the next step. Sometimes I do too many things in one step, and if people haven't seen trig in a while, it confuses them. Okay, are we okay here? So now let's rewrite the tangent as sine 3 theta over cosine 3 theta. Okay, so here's where some of your wishful thinking is going to come in. You're going to be saying to yourself, I have sine 3 theta over a theta. I wish this was 3 theta. How will I get that to happen? Well, we can force it to be 3 theta. Double check first that you actually need for it to be. If you think about what's happening with this limit, if theta is approaching 0, you would have 1 over 0. So right off the bat, you've got a problem, and you're going to have to work on something. So let's go ahead and try to get this guy into the right form so that we can use that special trig limit for this. If I want sine 3 theta over 3 theta, then I need to have a 3 on this theta. I don't have that. So I'm going to multiply by 3 over 3 so that I can get this into that special form. And then we're going to rewrite it again, just kind of moving everything around so that it's a little bit clearer to us what we actually have going on in our limit. And by the way, just because maybe you do it a different way than I do, that does not mean that your way is the wrong way. I tend to just, I just kind of start somewhere and keep going and see where I end up. If you start somewhere else and end up at the same limit, that's fine. It does not mean that you did it the wrong way. With these trig problems, there are often a lot of ways of doing them. Some faster than others. Okay, so we're going to have sine 3 theta over 3 theta. So I moved this 3 into that theta. We have a 3 in front of the function that came from this 3 up here in the numerator. Then we have a cosine theta over cosine 3 theta. And as you work your way through each step, you should sort of be thinking mentally about your limit and thinking about, okay, like what if theta approaches 0, what's going to happen here? Well, the nice thing is that the cosine of 0 is 1, and the cosine of 0 is 1. 1 over 1 is 1. This is a special trig limit with the value of 1 because you have sine of an angle over that angle. And then you're multiplying it by 3. It's ready now to go into the limit. All we really had to do was just kind of work with our product and shift things around in their order, and then rewrite the tangent as sine over cosine. Then we just introduced 3 over 3. And we just kind of rearranged where everything went. Once we do that, we'll pop it back into our limit. If you want to leave that 3 in front as a constant multiple, you might find that to be the easiest way of looking at it, but you just don't want to forget about it, so that's up to you. And then you have sine 3 theta over 3 theta times the cosine of theta divided by the cosine of 3 theta. Now, once you have that, rewrite your limit. Don't forget to show me that you're actually taking the limit. And once you apply the limit, take off that limit notation. Sine 3 theta over 3 theta, as theta approaches 0, the limit is 1. And then cosine of 0 divided by cosine of 0 is 1 over 1. Your limit is 3. Are there questions on this one? Okay, 2 more trig limits for you. All right, F. Yes, the limit as x approaches 0 of 2x minus 5 times the sine of 3x over x. All right, so for this one, we have a difference here. We're not multiplying, we're subtracting. And when you subtract, you have to use this denominator in both terms when you split it up. It's not like when you're multiplying and you have to pick a denominator for it to go with. This x has to stay in both fractions. Remember, you can only subtract 2 fractions if you have a common denominator. So when you split this up again, what you're going to have to do here, and if you're not sure why, I mean, go ahead and do direct substitution. You get 0 minus 5 times 0 divided by 0, which is indeterminate. We're trying to get this guy in a term by itself so we can use that special trig limit. Split up your fraction, but you're going to have to do it such that that x in the denominator still stays on both terms. And I want to make sure we understand the difference. I get a lot of students who are like, I don't get it. How come when you're multiplying, you only use it once, and when you're subtracting, you have to use it twice? There's a big difference. Trying to come up with an example of when I did that. I'm trying to find it. I don't know. Oh yeah, it was right here. So notice with part A, we were multiplying, we were not subtracting. If we were subtracting, we would have had sine x over x minus secant x over x, but we were multiplying, so we only kept the x that one time. when you're subtracting or adding, you have to take that denominator and make sure it gets put on each term. Okay, so split this up. And then again, you're in a situation here where you have the sign of 3x, and you're wishing that you had 3x in the denominator so that you can use that special trig limit. Well, let's rewrite this again. First of all, the first term just becomes 2 because the x's will cancel. And if you want, you could even split this limit up into the difference of 2 limits. I mean, you don't have to, but you can always just write it that way if you feel like it's easier to look at. So this will be, oh, and you know what you could even do? You could take the 5 that's a constant multiple and move it out front. So I took this 5 off the sign of x and put it in front of the limit. And then if you're wondering to yourself, why can't I have a 3x here? Just force it to be a 3x. But remember, if you multiply in the denominator by 3, you also must multiply in the numerator by 3. If you can cancel them out, then you'll get back with exactly what you started with. So like I said, this is all just a series of rewrites so that you can get this into a form that will work for you. Questions so far? I'm going to rewrite this limit one more time before we actually take the limit. I'm going to take this 3, and I'm just going to include it in front with the constant multiple. 3 times 5 is 15. Just to make it look a little bit cleaner before we actually take that limit. Okay, so the limit of a constant is the constant itself. Remember that if you're sitting on f of x equals 2, you're sitting on that horizontal line. The limit is always going to be 2 because you're always going to be on y equals 2 all the time. So the limit of a constant is that constant. And then 15 times your special trig limit here of sine theta over theta, as long as theta approaches 0, is 1. So 2 minus 15 is negative 13. Questions on F? Okay, so G, do one more trig limit. This is the limit as x approaches 0 of, use a bracket here, the sine of x times the cotangent of x minus the cosecant of x divided by x. If you want, you can go ahead and pull that function out of the limit for a few minutes while you work on it. One thing you should be noticing right away is that you have a situation where you have sine x over x. There's a sine x in the numerator and an x in the denominator. It would be prudent to put those together in one fraction. So we use the sine x over x. And then for the cotangent of x, remember that you have that quotient identity for cotangent. It's the cosine of theta over the sine of theta. Then you have a reciprocal identity for the cosecant. The sine of x is 1 over the cosecant of x. Therefore, the cosecant of x is 1 over the sine of x. So here's your cotangent. Here's your cosecant. And then the sine x over x is in front. Before I finish this one, does anyone have a question so far? Okay. All right. Now that you have rewritten these into their sine and cosine counterparts, one thing you could do is notice that, wow, I have a sine x in both of these denominators, and you could combine those together. So we could say that this is cosine x minus 1 divided by the sine x, and you could combine those into one fraction. Remember, as long as you have a common denominator, all you need to do is subtract the numerators. And then you can notice that you have a common factor of sine x in the numerator and denominator. If you want, you could rewrite this by splitting up the order of your multiplication. And I swapped out the x and the sine x. And now you can see that, wait a second, sine x over sine x is 1. And you just have cos x minus 1 over x. So we took this expression, sine x times cotangent x minus cosecant x over x, and we rewrote it as cosine x minus 1 over x. And that is the form of our special limit, this first one, cosine theta minus 1 over theta. So go ahead and take the limit now as x approaches 0. Of the cosine x minus 1 over x. The O looks like a 0. The value of your limit is 0. Like I said, you should always try to use direct substitution first, but for a lot of these, you're going to end up getting an indeterminate form. I mean, sine of 0 is 0. Divide that by 0 and you get an indeterminate form. So most of these are going to require some work. The other thing we have to do in here is talk about limits for some transcendental functions. These are really very, very straightforward. There's nothing crazy here, so I didn't want to give you a ton of examples, but I did want to show you one of each just so that you've seen them. Any questions on G before I move forward? Let's go here. Hold on. You can see the excellent. All right, so let me give you a definition here for these other two limits. One of them is the limit as x approaches c of a to the x is a to the c. This is for an exponential function with really any real numbered base. So this is for a and c being real numbers. A has to be positive, and a cannot be equal to 1. So we have that result for an exponential limit. Again, just applying direct substitution. We'll have another one for the limit of a log function, log base a of x. Well, again, you're just replacing the x with c. And this is for a and c being real numbers. C and a both have to be positive. And a cannot be equal to 1. I'm going to make a note because some of you haven't seen logs in a while. The natural log of x is equal to the log base e of x. And since you know that the same rule will apply for natural logs. So we can also say then that the limit as x approaches c of the natural log of x is just going to be the natural log of c. In this class, we'll be dealing more often with natural logs than logs with other bases. Example 3, find the limits. The first one is the limit as x approaches 0 of e to the x minus 1 divided by 2 plus e to the x. I'll leave that there. Okay, so and pretty much all of these, you're just going to be using direct substitution. You just need to remember how to evaluate these, but you can also use your calculator for these exponential expressions. We're going to be looking for the limit here as x approaches 0. So you can use direct substitution with these exponential forms. That's what you were told here in this first definition. The limit as x approaches c of a to the x equals a to the c. In this case, you're just dealing with a base of e, other than some other real number. So you'll have e to the 0 minus 1 divided by 2 plus e to the 0. Now remember that whether it's e to the 0 or 2 to the 0 or negative 5 to the 0, any real number to the 0 power is 1. So this gives you 1 minus 1 divided by 2 plus 1. And again, your calculator would have told you the same thing, but we should get very familiar with e to the 0. You're going to be seeing it a lot. Now, don't panic because you have 1 minus 1 in the numerator. That's okay because the denominator is not 0. And 0 divided by a real number is 0. So you don't have an indeterminate form here. You have an actual answer here of 0. So like I said, these should be really straightforward. And then for B, oh, does anyone have a question on A before I do B? We're looking at the limit as x approaches 1 of the natural log of x divided by 2e to the x. And again, I gave you a limit having to do with a log base a of x, and then we noted that a log base e of x was just a natural log, so we can use that theorem here, or that definition, I should say, with direct substitution. Everywhere you see x, replace it with 1. You have the natural log of 1 divided by 2e to the first power, so just 2e. Okay. Here's this little side note. Officially, if I asked you to find this limit and you wrote it like this, fine. You did what I asked you to do. It's pretty much simplified. It's done. However, there are a bunch of different ways of writing this. And if you see an answer in the back of your book, for instance, if you're doing extra problems, or if WebAssign ends up giving you some sort of default correct answer and you're like, wait a second, I don't know how they got that. And by the way, WebAssign is very liberal with giving you credit for unsimplified answers. So I'm sure they would be completely fine with this. But some teachers might consider this unsimplified. Like I said, I'm okay with this. But if you see it written in another variation, I want you to see where it came from. If you don't remember, and we're going to be using this more often from college algebra, you have rules for if you're taking the log of a quotient. Log of a over b is equal to log a minus log b, whether it's a natural log or a log of any other base. So that's something that you learned in college algebra, and you can apply that here. So we could have said, okay, well, this is the same thing as the natural log of 1 minus the natural log of 2e. Okay, so you could have simplified that, but then there's another rule that says that the log of a product, the natural log of A times B, is the natural log of A plus the natural log of B. Technically, 2 times E is a product, and that can be split up again. So you could actually then say, okay, well, we have the natural log of 1 minus, and then this would have to be put in parentheses because you'd be subtracting off more than one term, the natural log of 2 plus the natural log of E. And then you'd have to simplify that quantity. So there are a lot of different ways of breaking this down. The natural log of 1 is 0. You can put it in your calculator if you're not sure, but that's something that we're going to be using quite often here. So you'd have 0 minus.
Could you try again?
Thanks, Siri. She always thinks I'm talking to her, but I'm not. I don't know how that happens. It just started happening like a week ago. Distribute your negative sign. You'll have negative natural log 2 minus the natural log of E. And the natural log of E is 1. Again, you could put it in your calculator, but that's an identity that you learned back in college algebra. So you would have something like this as the answer, or something even like this. And there are even other ways to arrive at this conclusion. I say this to tell you that if you get an answer that looks like this, and somewhere else you see an answer that looks like that, you're going to look at this and say, whoa, I was way off base, when really you weren't way off base. There are just a lot of different ways to rewrite this to get it in a much different form. So I just really want you to be familiar with that in case you come across a key somewhere where you have it written in this form and you're not sure how to get there. I mean, you could have gotten here the same way by taking the natural log of 1 over 2e and rewriting it as the natural log of 2e to the negative first power. It's really just the reciprocal, right? 2e is the whole expressions in the denominator. And then you have a power rule that says that the natural log of m to the p is p times the natural log of m. They might have shown you these with different variables, but that would apply here also. So then you could have said, okay, well, this is just the negative natural log of 2e, and then you could have split it up again, so on and so forth. So, and really at that point, you're basically just right back here. 0 minus ln 2e is just negative ln 2e. And then you could, go forward. But I just wanted you to be familiar with these different ways of writing logs because it's going to come up again. And for some of these, we're going to have to rewrite our expressions using some of these algebra rules. In this case, like I said, this is fine with me. I just want you to be aware. Okay. All right, that's all I have to say about 1-4. Questions on 1-4 before we work our way into 1-5? Okay, I'm going to start 1-5 now. I will finish it on Wednesday. Yeah, so I'm thinking now, see how the plan kind of evolves as I work. I'm thinking now we'll probably test over 1-1 through 1-5. I'll start 1-5 now. I'll finish it Wednesday. So technically, yeah, whatever I finish Wednesday will also be on your exam, but it's not like it'll be brand new material because I'm starting it now. And then the 2-1, 2-2, I usually kind of combine those sections because they really work together. So I'll just do that for your asynchronous. We don't have to put a ton of focus on it on 2-1, 2-2 because most of what you're going to be doing in chapter 2 will have to do with derivative rules and not doing things the long way. So I don't usually put a whole ton of focus on 2-1, 2-2, just sort of enough so that you kind of get the gist for the topic. 1.5 is about infinite limits. and limits at infinity. And asymptotes. Now, these are topics and concepts that we've just kind of touched on over the last week. But we're going to get into them in more detail here. So we sort of, or I guess I mentioned that in the asynchronous work, I was sort of talking about limits as they pertain to these asymptotes, where all of a sudden, like, you have this infinite discontinuity. So we're really going to go through this concept of an infinite limit today. And then next time, a little more focus on the limits at infinity, just talking more about horizontal asymptotes. Okay, so example 1. Find the following. I'm going to give you a graph, and I'm going to try to draw this. So there's kind of a lot going on here. I'm going to try to be very descriptive as I go through it. We're only going to need to go out as far as like 3. So maybe we'll go 1, 2, 3. And -1, -2, -3. And 1, 2, 3. 1, 2, 3. Okay, I'm going to have a dashed line going through y equals 2. It's dashed. I'm going to have a dashed line going through y equals -3. I'm going to have dashed lines at x equals positive and -2. And make sure everyone has a chance to catch up. All right, I'm going to build this from left to right. I'm going to have a function going through the point at -3, 0. And it is going to approach my dashed line. And it's going to approach this dashed line. I'm going to take another function and I'm going to squeeze it in between my next 2 asymptotes. I feel like we should dash the y-axis too. I'm going to try to dash that. You know, it's kind of hard to dash an axis. You have to offset your dashes. All right, so I'm going to run this function through the point -1, 0. It's going to go kind of like this. Now, this is a purely hypothetical function. It's really not something that you would see. Clearly, it's some sort of piecewise function. I'm going to put an open circle at the origin and then run this up. Do whatever you want as long as it's approaching your dashed lines. And then we'll do something similar on this side. If you want, pick a point to run it through. It's not the end of the world. Kind of like this. Anyway, it's always hard to have students reproduce these graphs, so I try to do it slowly, piece by piece. All right, now I'm going to ask you a series of questions about the graph. This is another situation where in class I would see if everyone was still writing or if they were all just sitting there. So I can't tell, but it looks like the two people I see that you're not writing. So I'll proceed. The first thing I want to ask you is the limit as x approaches -2 from the left of our function f of x. And I didn't label it, but I think it's pretty clear to see that -2. Oh, I actually did label it down here. That's okay. So as our function approaches -2 from the left, we're looking for the limit. Now this is going to be a little bit different because in this case, as you're approaching -2 from the left, you're seeing that the behavior of y actually continues to head downward. And we're never actually going to reach -2. It's just going to approach this vertical asymptote. You learned about these in algebra, and it's never quite going to touch it. But the value of y is going to keep heading down and down and down and down forever. So we would say that this limit is -infinity. And I know it's weird to say equals -infinity, but technically the limit is -infinity, just means that your function values are heading down towards -infinity. So when you have these dashed lines, they're going to represent asymptotes, and you're going to approach the asymptotes, but you can't, well, vertical asymptotes you're going to approach, but you can't touch. We'll talk about how that relates to horizontal asymptotes in a minute. And then I'm going to ask you to find the limit as x approaches -2 from the right of f of x. So as x approaches -2 from the right, well, now I'm looking at values that are to the right of -2. And as the x value gets closer and closer and closer to -2, you can see that the y value continues to go up and up and up and up. And even though it looks like it's vertical, it's still incrementally moving left by very, 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 very small amounts. So it's not actually vertical. It continues to get closer to the asymptote very slowly. But the value of y keeps going up and up and up forever. The limit is infinity. Now, just so that we understand this here, if I actually asked you to find the limit as x approached -2, well, as I approach -2 from the left, we said the limit was -infinity. As I approach -2 from the right, we said it was positive infinity. So this is a DNE situation. The limit does not exist. I'm going to do something similar at 2 in a minute. So if you feel like you want to compare and contrast, hold on, because I have more parts to get through. But as it pertains to -2, does anybody have a question on the limits that we found on this graph? Okay. So I also want to do the same thing as we approach 0. So let's look at the limit as x approaches 0 from the left of our function. So as I approach 0 from the left, I'm heading towards 0 on this little curvy piece that's heading downward. But as x approaches 0 from the left, the y value continues to go down and down and down forever. So we would say that this limit is -infinity. And then very predictably, I'm going to ask you to find the limit as x approaches 0 from the right. So as x approaches 0 from the right, even though the function value doesn't exist at 0, we would say that the limit is 0 because the actual value of y is approaching y equals 0. So as x approaches 0, y also approaches 0. So y is heading down just towards the x-axis, which is y equals 0. So remember, the function value doesn't exist. That's fine. Doesn't mean the limit doesn't exist. The limit does exist. But we're in another situation here where if I actually ask you to summarize the limit as x approaches 0 of your function, you would have to tell me the limit does not exist. The left and right limits don't agree. One of them's heading off towards negative infinity. The other one is heading to 0. So really kind of breaking apart these one-sided limits here. Let's look at, I'm trying to fit this all in together so we can still sort of refer to the graph without getting too far away. G down here. This is the limit as x approaches 2 from the left. And since I'm running out of space, let's write the other two down so that you have them. We're also going to look at the limit as x approaches 2 from the right. And then I want to look at the limit just as x approaches 2. So that will be GHI. And notice, by the way, that I'm really only asking you about the interesting places on the graph. I'm not asking you what happens at 1 or what happens at -1. There's nothing exciting there as it pertains to infinity. But as I approach 2 from the left, my y values continue to go up. And as I approach 2 from the right, again, my y values continue to go up. In this case, both ways, as I approach 2 from both directions, the value of y continues to increase towards infinity. So for g and h, I can say that these limits are infinity. And students always want to know then, well, does the limit as x approaches 2 of f of x not exist? I mean, officially it doesn't exist, but we would say in this case that the limit is infinity, because in both cases, for the left and the right-hand limits, we're approaching infinity. So we would say that the limit as x approaches 2 is infinity. In this case, the limits agree, if you want to state it that way. Before you got to this section, if you would have seen something like this, you would have said DNE. Now you're expected to tell me that it's infinity. But note the difference. At -2, the limits did not agree. On one side, you were approaching negative infinity. On the other, it was positive. So we said DNE. For +2, as you approach x from the left and the right, in both cases, you're heading up towards positive infinity. So we can make the conclusion that the limit as x approaches 2 of f of x is also infinity. I'm going to ask you 4 more questions about this graph. Does anyone have a question so far? I guess I could zoom out a little bit too, but I don't want anyone to have a hard time reading it either. And I can only zoom out so far. JKLM. Think about my alphabet here. J. Let's talk about the limit as x approaches infinity of f of x. And for K, we'll talk about the limit as x approaches negative infinity of f of x. Now, when you're talking about a limit being equal to plus or minus infinity, you're thinking about how that pertains to vertical asymptotes. But when you're talking about a limit as x approaches plus or minus infinity, now we're thinking about horizontal asymptotes. What you're looking at is, what is the behavior of the function as x gets increasingly large or as x gets increasingly small? So for J, you're focusing on very large values of x. If you're looking for values of x that are getting very large, we're focusing on what's happening in this segment of the graph over here on the right. Now you can assume here that as x continues to increase, the value of y is going to continue to head towards this horizontal asymptote. So we had this dashed line at y equals -3, and this is controlling the behavior of your function as x approaches these very large values. And I know you might be thinking, well, how do I know it doesn't eventually cross the dashed line? Well, because the dashed line is a horizontal asymptote, it's controlling the end behavior of your function. You did learn about these in college algebra. It might have been a long time ago, but you have seen them before. As x gets very large, y is going to approach but never touch -3. So we would say that the limit as x approaches infinity of f of x is -3. And we're going to do something similar as we approach values of x that are very small, as x approaches -infinity. Any questions on J? So for K, we're going to do the opposite. We're going to look at values on the left-hand side of the graph as our value of x is getting increasingly small. So as x gets smaller and smaller and smaller and smaller, the values go left, 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 left. The value of y is approaching, but is never going to touch y equals 2. So it doesn't matter what happens over here. Who cares? We're only worried about what happens as x continues to get smaller. And you can see that the behavior of this function would just continue on its path, approaching y equals 2. So we would say that the limit as x approaches -infinity of f of x is 2. Now, sometimes students get confused because you're always told, for instance, that you cannot cross a vertical asymptote. Well, that's true. But then they're like, well, how come you can cross a horizontal asymptote? A horizontal asymptote is basically there to guide the end behavior of your function. But a lot of times you see instances where in the middle of your function, you might cross a horizontal asymptote. I mean, like you have this horizontal asymptote going through right here, but your function crosses it here, here, here. That's okay. The horizontal asymptote is guiding the behavior as your function gets increasingly small or increasingly large, or I should say your value of x gets increasingly small or large. So you can cross a horizontal asymptote somewhere in the middle of your graph, but not at the ends. And you're going to see that again in curve sketching, where you might be like, wait a second, I have a horizontal asymptote. How can I cross it? That doesn't make sense. You can, just not at the ends. I also just wanted to add on 2 last questions here. The first one will be L, find all vertical asymptotes. And when you find asymptotes, you list them in the form of an equation. So your vertical asymptotes, I already listed in the form of an equation for you. There are these dashed lines that go vertically through your graph. One of them is x equals -2. The other one's x equals +2. And officially, we did dash the origin. So, or we did dash through, I should say, x equals 0. So we'll include that as an asymptote, since we do see that the behavior of this function is approaching but never touching. So we'll say x equals -2. X equals 0, and x equals +2. Those would be your vertical asymptotes. And then as far as your horizontal asymptotes are concerned, these are just your horizontal dashed lines. Note that you don't actually have a horizontal dashed line on the x-axis. The x-axis is solid. You don't have any values of y that are approaching the x-axis in either direction. So we don't have the x-axis being a horizontal asymptote. We just have y equals 2 and y equals -3. So we'll always write these in the form of an equation. Okay, so that was a really long example with many parts, but hopefully it was very comprehensive and covered all the bases. Does anybody have a question on example 1, A through K?
Yeah, shouldn't it be M instead of K?
Oh yeah, why did I write K twice? I don't know. Thank you. I don't know why I did that.
It's all right.
Thanks. Then does anyone have a question on A through M? Not just A through K. All right. Terrific. Let's look then at some more infinite limits where we are going to have to use a table, because I know you guys love those. Just kidding. Nobody likes that. All right, example 2. Nice. Find the infinite limits. So for example 1, I gave you a graph and I asked you a bunch of questions about the graph. For example 2, I'm going to just be giving you some limits of functions, and you are going to have to justify your responses. Now, I'm going to be asking you something like this on an exam, and I'm going to specify how I want to see your answer. But for something like this, I would show it with a table. If I did not specify, technically you could look at your graphing calculator and tell me what the limit was, but you would actually have to say, I looked at my graphing calculator. When in doubt, if you looked at your graphing calculator and obtained a solution, first of all, make sure that that's a method that is okay for that question, because for the most part, I want you doing things the way we did them in class. So like, for instance, you know what happens sometimes? Students have this quadratic equation program in their calculator. So they'll have an example on a test or a problem on a test where they have to solve a quadratic equation, and then they'll just give me the answer and show me no work. And then I'm just like, what the heck? I don't even know where this came from. Like, where did you get this work? And I don't know. And then I would occasionally have a student who would write, I obtained this from my graphing calculator. Well, that makes sense to me because I know that students sometimes have those on their graphing calculator, and I didn't technically say not to use it, so that's okay. And then I get where it comes from. But when all I see is an answer and no work at all, it makes me wonder. And then I start to question that student's integrity. So make sure that you're writing down where you obtain things if it's not clear. So if I did not specify a method for doing this, yes, technically you could look in your calculator at a graph, but you would then have to tell me how you arrived at that conclusion. However, for something like this, I would very likely specify that I want you to use a table to find this infinite limit. So I'm going to show you how to do that right now. Okay. And by the way, that situation with the quadratic formula, it happened in a Calc 2 class, and honestly, I'm not testing you guys on your ability to solve quadratic equations. I mean, it's a really useful skill, but it's certainly not something I want to like ding you for on an exam. So it's not the end of the world. Just say where you got your information. I'm going to put my table down here. Okay, so I'm going to approach -3 from the left, and I'm going to look at what happens to the y values as I do. Now, I've already stated in the example directions that I want you to find the infinite limit. So you know that there's going to be an infinite limit. If you weren't 100% sure, well, look at your denominator. -3 is not in the domain of this function, and I'm asking you about what happens as x approaches -3. So I'm looking for what happens at that place where your function does not exist, where the function value is not defined. You're expecting some sort of infinite discontinuity here, so you're expecting a vertical asymptote. Reason being, you can't cancel anything out here to create a removable discontinuity. It's got to be some sort of infinite discontinuity. So let's go ahead and approach -3 from the left. So we're looking at values that are to the left of -3, so further away towards the left on the x-axis. So you might want to approach from a little farther away and then get closer and closer. That's probably close enough. If you feel like you need more, maybe include another decimal place. It's kind of up to you. Oh, sorry, I didn't write my 1 here. It's kind of up to you to figure out if you're close enough to really be able to make a prediction, because everyone's going to use different values. I mean, for the most part, people use similar values, but it's up to you to make that final decision of, am I close enough to really definitively state what's happening with this function? So we're going to get super close to -3, and then we're going to come up with a prediction for the limit. And you can put these in your calculator. And I know the funny part about this is as soon as you put these into your calculator, you're like, okay, well, I just had to graph the function anyway. So I know you're going to be able to see the graph anyway. I get it. So you're wondering, why do I have to do all this? You're expected to know how to do it. I don't know. We got to jump through a lot of hoops in life. So your function is x divided by x plus 3. Make sure that you put parentheses around your denominator. And then you're going to go to your table, and you're going to enter your values, -3.1, -3.01, -3.001, -3.0001. And you're going to look at what happens to the y values as x gets closer and closer and closer to -3. Notice that you went from 31 to 301 to 3001 to 30,001. And that's definitely enough data to make a prediction here about what is happening with your function as x approaches -3 from the left. Go ahead and fill these values into your table. 31, 301, 3001, 30,001. These values are getting very, very, very large. And you could keep getting closer and closer and closer to -3 if you'd like. But this, I think, is enough to make a prediction and say that these values are getting increasingly large as we get closer to -3. So we could say that at -3, our function must be approaching infinity. So we would say infinity. And if you'd like, since we've already done this in the table, you can look at the graph and just sort of get a visual on what's happening. I really love to get a visual representation along with the tabular representation. I think it's really helpful to see both. Notice that as we expected on the graph, we have this infinite discontinuity when x equals -3. It's not removable, definitely not removable. Infinite discontinuity, might as well just state it at x equals -3, non-removable. And then you can see as we approach -3 from the left, you're looking at what happens to the value of y. Well, as we get closer and closer and closer to -3 from the left, the value of y actually increases towards infinity. You can see now that that's the only thing that can possibly happen. So you might want to make a side note after looking at this graph that the limit as x approaches -3 from the right, now that we know something about it, if you're looking at these function values as you approach from the right, they're actually heading towards -infinity. And I'm going to say I saw this from the graph. Now, technically, I didn't ask you that, so you don't have to say that on a test. You would just have to fill in your table and tell me the value of the infinite limit. But because the limit as we approach from the left and the right is not the same, we would say that the limit as x approaches -3 for our function does not exist. Sometimes I just like to add a little bit to the example so you get a more complete picture of what's happening. Okay. Questions on A? Hmm. I feel like we've done a lot of this tabular stuff. Do you guys want to see another example? You know, I will do a trig one because I sometimes think students get stuck on some of these pi values. So let's do a trig one. This is the limit as x approaches negative pi over 2 from the left of the secant of x. Parentheses are non-essential. I just wanted to make sure that this didn't look like negative secant x. So this is going to work the same way. Remember that the secant is going to have, you probably don't remember this, but I'm going to remind you right now. The secant function is going to have vertical asymptotes anywhere that the cosine function has an x-intercept. So the cosine function has an x-intercept when its value is 0, and the cosine is 0 at integer multiples, or I should say odd integer multiples of pi over 2. So you're expecting here some vertical asymptotes. You're trying to figure out what's happening as we approach this one from the left. Now we're going to enter this in our calculators, but we're going to have to enter it, remember, as 1 over the cosine. Now, I also want to show you how to enter this in your table. Sometimes students get a decimal representation for this, and then they start working with their decimals. And if your number sense isn't great, then you're going to get really lost on how close you are using this irrational number. So what I would suggest to you is when you're writing your table for this, make life easy on yourself. Don't work with all these decimals and try to manipulate them. You're going to end up in a big mess. Take the value that you're approaching, which in this case is negative pi over 2, and then just get closer and closer and closer to your value. So if you think about what this looks like graphically, I mean, we're looking at negative pi over 2, and you're approaching it from the left. So if I'm approaching this value from the left, then I'm looking at values that are less than this, but we're going to get to be closer to this. So I'm gonna narrow it in, but I'm gonna start out by values that are a little more less. We're gonna start out with values that are much less than this one, and then get closer to it. So when you start out looking at these values, maybe do something, the same thing that you did up here. It's just gonna look different because it's negative pi over 2. So we went to the left of this value about 0.1. Do the same thing here. Go to the left about 0.1. And then get closer. Stay to the left, but not quite as far to the left. Maybe 0.01. And then again, you're staying to the left, but you're getting closer to your value. See how that works? So don't say, okay, well, pi over 2 is approximately this value, and work with the decimals. You're going to have a harder time there. We're going to do it this way. It'll be much easier. And of course, if we were approaching from the right, we would have done the same thing, except we would have added these values on instead of subtracted them. So we'd be looking for values that are greater than our function. Question so far? So when I'm entering the secant of x, your calculator, as far as I know, I'm always finding out new things every day, does not have a secant function. Take this as 1 over the cosine of x. And then go to your table. And then you can just enter these values directly. Negative, your pi button, if you're not sure where it is second, and then your caret. So you can see second caret gets you pi. Divided by 2 minus 0.1. Now your calculator is going to, of course, approximate that, but you're going to enter it exact. If you hover over it, it'll give you that full, not full, but a much closer approximated decimal. But don't worry about that. All you need to do is focus on entering the exact value and then take that decimal off each time. So negative pi over 2 minus 0.001. Yeah, the only thing is you have to remember which ones you've done so far. No big deal. Negative pi over 2 minus 0.0001. And this is definitely enough data to show you that your values are decreasing as you head towards negative pi over 2. And I think the tabular approach for these trig functions is actually more useful, because when you're talking about values like pi over 2, some students have a hard time even locating where that is on their graphing calculator. So they're like, I can't tell graphically because I don't know what the tick marks are. So the tabular representation will definitely be more helpful in that instance. So you're at negative 10.02, negative 100, negative 1,000, and negative 10,000. So we can definitely make the conclusion in this case that the limit would be negative infinity. And we can look at that on the graph as well. Now, my graph right now is in Zoom Standard. Zoom Standard is going to have x going up to 10, left to negative 10, and then y going up to 10 and down to negative 10. If you want to zoom trig, hit the zoom button, and zoom trig is number 7. So you can hit number 7, and that will give you multiples of pi over 2. If you are not sure what the tick marks are, zoom trig is always, it always gives you these same ones. You're going to go pi over 2, pi, 3 pi over 2, 2 pi. If you're not sure, though, you can always trace it, but it doesn't make sense to trace it if you don't know your trig values. So it'll always kind of tell you where you are. So x is 0, and then if you know, for instance, that pi is 3.14, well, pi over 2 is, like half of that, which is about 1.7. So as you trace, you can kind of see your cursor is going to go up. And then you're like, okay, I know I'm approaching 1.7 now. So this has to be pi over 2. And then this has to be pi. And then as soon as it gets to a point where it doesn't want to compute anymore, it's just going to push you on to the next curve. And you'll see that when the y value gets small again. So clearly it's up really high because y is at a super high number. If you cursor over it again, y is going to get really small again. Well, not super small, I guess, but pretty small, because now it's bumped you onto the next curve. And then as you approach, you can see that you're at about pi, 3.1415927-ish. And then that must, of course, be pi over 2. So as we approach pi over 2 from the left, you can see that the function values increase towards infinity. As you approach from the right, oh, sorry, we were looking at negative pi over 2, not positive pi over 2. So if that's pi over 2, this one is negative pi over 2. And as we approach negative pi over 2 from the left, your function values are approaching negative infinity. If we were to approach from the right, we'd be looking at positive infinity. But this is what we were trying to find as we approached negative pi over 2 from the left. Okay, so that was a trig problem. We found our limit using a table. I have 4 minutes and I don't want to waste them. So I'm going to give you the next definition and we're going to use it next time we are here. I would like for you to write it down now because that's going to save us time and it will already be in your notes for the next class. All right, so limits at infinity. We're going to talk next time about horizontal asymptotes. And a lot of this will be review, honestly. That's another reason why it's not too big of a deal to me to test you over it on Thursday, because technically you've already worked with horizontal asymptotes in algebra. All right, limits and infinity, end behavior. All right, so we have some properties here. One of them, the limit as x approaches infinity of x to the n is equal to infinity. So infinity to the nth power, we're going to say is equal to or approaching infinity. This is true if n is a positive integer. Interesting. We have another conclusion similar to that if x approaches negative infinity of x to the n. In that case, we end up still getting infinity. And this is if n is a positive even integer. And if you want, you can think about functions that you know that follow this similar behavior. Like for instance, if you were talking about x cubed, well, if you're looking at that cubic function and you have x approaching infinity, well, the function value is also going to approach infinity. If you are approaching negative infinity, but you have n being a positive even integer, that might be something like x squared. So for x squared, you know you have a parabola that goes up in both directions. As you approach positive or negative infinity, your limit would be infinity in that case. Another conclusion would be for odd integers. Again, that situation with x cubed. As x approaches negative infinity, your limit would be negative infinity. And this is for if n is a positive odd integer. So this is sort of just a recap of end behavior, which you learned in college algebra. You were asked to find the end behavior of a function. We're going to look at that again when we're curve sketching. We also have the limit as x approaches infinity of k over x to the p power equals 0. And the limit as x approaches negative infinity of k is some constant, over x to the p power is also equal to 0. Now this is if p is positive and rational. A rational number, remember, is one that can be written as a fraction. Sorry, I'm running out of space on my desk here. And k is a real number. Provided x to the p is defined for positive x. Or I'm sorry, for negative x. So we are going to work with these conclusions next time. I wanted to just sort of give you these now. It's a recap from what you learned about in college algebra, just kind of talking about what happens to the y value of your function as x gets increasingly large or increasingly small. And all of that is just really dependent on the degree of your function. Remember, the degree of your function is controlled by this exponent n. So we'll pick up here on Wednesday and we'll finish talking about horizontal asymptotes. And then we'll have your test on Thursday. I'm going to put up some homework for you to finish off 1.4 and to work on what we've talked about so far with infinite limits in 1.5. That is all. I hope you all have a wonderful evening. If you have questions, feel free to send me an email, or I'll be on for like 5 more minutes if you have anything pressing. Stop my recording. I'm going to put up your homework right now.